Let's wait for 2 3 minutes. After that, I will start. Let me share the screen. So this is the second week, uh, problem solving session for the mathematical methods of physics. So today, in fact, in the last lecture, we have studied about the augmented matrix and the actual matrix in order to understand uh, the set of equations, linear equations are there. So we calculated the rank. Now the question is that why are we calculating rank? That is what we will be dealing today. We will see the concepts of determinants, the properties of determinants, and we will solve some numerical type questions in order to understand all these things. And once this is over, we will talk about the linear dependence and dependence again, and span basis is very important, and then some topics like Gram-Schmidt, uh, orthogonalization, orthonormalization, and so on. Some operators are there like adjoint operators, some linear operators, how they are being used. A little bit of that is I will try to uh, give, uh, and mostly we will solve some questions on these basis span and all these rank related things. Okay, so these are the particular things which we will look at. So just show you. So let me just write down what we will be focusing on today. So, so one is that we will see using rank. of the matrix, or using rank calculations, I would say, because not only we will calculate the rank of the matrix, but we will also calculate the rank of the augmented matrix. We will try to understand or try to understand the solutions, about the solutions of a set of equations, linear equations. So this is one of the things. Second is that we will use the concept of determinant, and in fact, we will relate this determinant using the determinant how to calculate the rank of the matrix and all those things. Particularly, we will deal with the properties of the determinants, and we will solve some questions. Questions on this also will be there. And number three is that the base concept is that we will talk about the basis and span. Okay, about this one question is there to understand the concepts, and then we will go towards subspaces and other concepts like your some operators and all these things. Okay, so these are the particular basic things which we will be talking today. Okay, to start with, so suppose you have some systems of or a system of linear equations. Okay, system of linear equations you have. Okay, something like this: a1 x1 plus b1 y1, or let me just keep the unknown as it is. So a1x plus b1y, say plus c1 equal to 0. This is, I'm just using two unknowns for the time being. But when we solve some questions, we will see that there may be possible that there are three unknowns and three sets of equations. And then you have some a2x plus b2y plus c2 equals 0. Say, suppose for an example, this is a set of linear equations, right? So this is the starting point of why we need the rank of the matrix. What is the usefulness of calculating the rank of the matrix as well as the augmented matrix? This is what the question which comes out from the last class, that we have calculated the rank of the matrix as well as the augmented matrix. What is this useful? Where is this useful? So that is what the thing which we will be discussing today. Okay. So what happens is that uh, if you have this kind of a system of linear equations, there are three sets of solutions broadly categorized. One is that you may have, number one, you may have inconsistent solutions. Inconsistent solutions means you might have no solution at all. You have two equations where there is no solution. For example, let us consider this a graph I am plotting. So this is suppose this some x y. Okay, and you have a line like this as representing any one of the equations. Let us say based on the a1, b1, and c1 values. Similarly, you have another uh, line or the another equation graph which is like this. Okay, so these are parallel lines. They never meet. So if they are never meeting, then you don't have any common solution. That's why we are calling this as a no solution kind of a category of these set of linear equations. Okay, so this is one of the things. Okay, so this is one of the category of the solutions of the set of linear equations. What about the next, the second category? Second category is that you have a unique solution, a single solution and a unique solution. Okay, this is the second category. You have a unique solution. So when is it possible? Let's see. Suppose this is again your xy coordinate system. This is x, this is y, suppose. And one of the equations which I have written here, so written there in this. So in one of the equations, if I put a1, b1, c1 in such a way that it gives you something like this. So, something like this. Okay? This is one of the equations. And the second equation, based on the values of a2, b2, and c2, you can draw a line like this. Now see, there is an intersection, and there is a point of intersection between these two equations. And we can say that this is the unique point where these two equations are crossing each other, intersecting each other. That intersection point is nothing but a solution to this set of linear equations. Okay, so this is one of the category of the possible solutions of the set of linear equations. One category is no solution, two parallel lines based on the values of a1, b1, and c1, whatever it is. Second is the unique solution. Again, we change the values of a1, b1, c1 in such a way that they are intersecting at a particular point. That is the unique solution, one and only one solution. Okay, this is the second category. What about the third category? The third category is you have infinitely many solutions. So when is this possible? Infinitely many solution or infinite solution, whatever you wanted to write. Okay, infinitely many solutions. When is it possible? So let's see. Again, you plot a xy coordinate system. This is x, suppose this is y. Again, you have these two sets of equations which I have written. You have freedom to choose a1, b1, and c1, or a2, b2, and c2 for the second equation. And based on that, suppose you found out this is the first line, and the most importantly, the second line is exactly overlapping this. So you can understand when one line is overlapping on the other line, each and every point is a solution. So, and you don't know how many points are there. So there are infinitely many solutions possible in this case. Okay, so these are the categories which you can find from a system of linear equations. This is a graphical representation. Remember, I am not talking about the rank right now. This is a graphical representation. So what are the different categories possible for these sets of equations? Okay, so these three basic categories are there. Now the question is what we were asking, that how the rank, how the rank of matrix M. Now I will write the equation, then only you will understand. The matrix M and the augmented matrix A help or to find these categories. Okay, so this is the question we are asking from the beginning. Okay, that how the rank of the matrix M and the augmented matrix A help to find these categories. So what we are trying to say is that suppose you have M as the matrix, X is the matrix of the unknown variable, and is equal to suppose some resultant R. Okay, so your M is the original matrix. A is the augmented matrix, which consists of M on the left hand side along with R together. Okay, so this is the augmented matrix. So when you have a set of equations which can be written in the matrix form like this, then if you calculate the rank of the matrix and if you calculate the rank of the augmented matrix, which we have done using row reduction techniques and finding out the number of non-zero rows and calculating the number of non-zero rows as the rank, then what is it? Well, how these are useful in particularly determining these categories. Okay, so for this we have certain observations. Based on that we can see. So suppose this is the rank of M. Okay, rank of M, if it is less than rank of the augmented matrix, then we can say that there is no solution. Okay, then we can say that there are no solution present. The category of this one, kind of a parallel lines thing, okay, is inconsistent or it has no solutions if the rank of the matrix is less than the rank of the augmented matrix. This is number one observation. Second observation is that the rank of the matrix, if it is equal to the rank of the augmented matrix and is equal to the number of unknowns. Unknowns means these are the unknowns. See, you have A1, B1, C1, as I have told you that you have the freedom to choose the A1, B1, C1, and A2, B2, and C2. Only thing which you are calculating here is the X and Y. Right? So these are the unknowns. So for the unknowns, if the number of unknowns is n, then if the rank of the matrix is equal to the rank of the augmented matrix, which is equal to n, then there is a unique solution. That means there is some kind of an intersection possible. Okay, there is a unique solution. And number three is the infinitely many solutions, right? So that is, see, the same condition is repeated. R matrix, the rank of the matrix is equal to rank of the augmented matrix. But the problem is that is equal to say some R, which should be less than N. So suppose in this case, for example, there are two unknowns, and suppose my rank of the matrix comes out to be 1, rank of the augmented matrix also comes out to be 1. They are equal, but 1 is less than 2. That means there are infinitely many solutions. Okay, so these are the, based on observation, these are the categorization using the rank of the matrix. Okay, infinitely many solutions. So these are the important thing. So yes, so this is the main message from the rank of the matrix. How to understand the that whether the solutions are unique or whether there are no solutions or there are infinitely many solutions. We can understand from this. Okay, so let me just uh, write it down properly. So n is the number of unknowns such as your x, y, or z for some reason. Because there are, it may be possible there are three unknowns. We will see one question. We will see from this. So that will be clear. Okay. So this is how it is, and yes. So that's all. So now, if we just go to a question and try to see that how we can relate to this. So for that, let us see one question. Okay. So we have, unlike the first generalized case, I have now something like this. So 2x minus 3y plus 7z is equal to 5. 3x plus y minus 3z is equal to 13. Okay. Next, you have 2x plus 19y minus 47z is equal to 22. Okay, so this is how it is uh, there. The most important fact is that if we just take this and this, you can see that to the left of this x, same value is present. Generally tells you that the slopes are same. So kind of giving a hint of a parallel lines, but we can't say right now. Okay, let's go ahead first to understand the rank. So the first thing is that how many unknowns are there? There are three unknowns, right? So initially, looking at the question, we should look for how many unknowns. So therefore, there are sorry, yes. So there are three unknowns x, y, z. Okay, this is one of the point. Second point is that suppose you have a matrix M, because we want to write it in terms of this mx is equal to some r. So it will be the M matrix will be 2 minus 3 7, 3 1 minus 3, and 2 90 minus 47. Okay, this is your actual matrix. So, and what about X? X is nothing but simple XYZ is 3 by 1 matrix, and R, the resultant, is 5, 13, and 22. Okay, so this is how we can write. So M into X is equal to R. This is how we can write the system of equations. Okay, now let's find out the rank of this M, the matrix M. Okay, so let's go ahead and do the reduction. Okay, so 2 minus 3 is 7, and you have 3, 1 minus 3, you have 2, 19, and minus 47. So what I will do is that I just write the steps which I have followed, and just I will write it down. The computation or the calculation of those steps, you can do it later if you want, or otherwise you can try on your own. Okay, so this is what I have done in order to reduce. So the first case is that I have done R1 as R1 by 2. So I am getting here 1, 3, 2. This is minus 3 by 2. This is 7 by 2. 1, 90 minus 3, 47. Okay, this is the first step I have done. Second is, of course, I have to reduce it, row reduce it. So the leading element should be 1 and all other column elements should be 0. That is what my main aim will be. Okay, so R2 will be equal to R2 minus 3R1, and R3 is equal to R3 minus 2R1. With this, I have managed to put this 100 here. This will be similar. This is 7 by 2. This will be 1. Uh, I'm sorry. This will be 11 by 2. Sorry. This will be 22. This is minus 27 by 2. And this is minus 54. So on applying these two operations, we will be getting this. Fine. Okay. Next is this next step which I have followed is that let's do R2 as 2 by 11 R2, because I have to put this element as 1. Okay. So M will be therefore 100. Here there is no operation because it is already 0. Okay. So here it will be 1. This will be 22. This will be what? This will be minus 27 by 11, and this will be minus 54 as it is. Next step. Next step is to put to change these elements as 0. So based on that, just put the thing. So it will be R1 plus P by 2 R2 and R3 minus 22 R2. All right. So these are the steps which we will be following to get the row reduction of the second column is also possible. So 0, 1, 0 we will get. What about these changes here? It will be minus 2 by 11. This will be minus 27 by 11. And this will be 0. All right. So we have got finally up to this. So you can see that the number of non-zero rows here is number 1 is this, and the second one is this. The third column is completely 0. Sorry, the third row is completely 0. So here we have to stop because we can't make it some 001 kind of a thing. Okay, so here we will stop and we will say that the rank of matrix M is Rm, suppose, that is equal to 2, because there is two non-zero rows in a row reduced echelon form. Okay, so this is what the steps we have followed, and we have also done this in the last class as well. Now let's go for the augmented matrix. What is that augmented matrix means? So I'm just repeating it. So augmented matrix is M along with the resultant R. Okay, so M you can write as it is, whatever is there. 2 minus 3, 7. You have 3, 1 minus 3. You have 2, 19 minus 47. And on the other side, you have to write the 5, 30, and 22. This is your this part 5, 13, and 22. The right hand side part. Okay, now you have to solve it again. So we'll see another important thing to uh, we'll discuss about that. So, but let us again row reduce this particular part. So actually, I'm doing an extra step. You don't need to do calculate this M and row reduce it separately and augmented matrix row reduce it separately. You can directly use this augmented matrix and do the row reduction technique. Based on that only, you can say that what will be the rank of the matrix M and rank of the augmented matrix. So no need to use this part which I have done earlier. You can directly start with this. Okay, but this is for the explanation purpose I have used it. Okay. So again, I will start with the same thing R1 as R1 by 2. You will see that most of the steps which I will be doing is exactly same as what I have done here in the in row reducing the matrix here. So it is exactly similar. Alright, so what we will do is that the next step is this. So here it will be 1, this will be 3, this will be 2, this is minus 3 by 2, this is 1, this is 19. Okay, this is 7 by 2. This is minus 3. This is minus 47. And you can just dot it with a line 5 by 2, 13, and 22. This is the augmented matrix after the first step of row reduction technique. Next step is same R2 minus 3R1 because you have to make these zeros. So R3 as R3 minus 2R1. So what you will have essentially the same thing. See 1 0 0. So it will be now minus 3 by 2, 11 by 2, and 22. This will be 7 by 2, minus 27 by 2, and minus 54. This will be here will be 5 by 2, 11 by 2, and 7. Okay. So same thing we are repeating. Again the same thing. R2 as 2 by 11 R2. Right? So this becomes then what? So it will be 1 0 0. This will be minus 3 by 2, 1 22. This will be 7 by 2 minus now 27 by 11, and this will be minus 54 as it is. Here there will be some change. For example, this is 5 by 2 as it is. This is 1 because I have multiplied by 2 by 11, and I think it is 11 by 2. So it's fine. And this is 17. Yeah. Now the next step again to convert these two as 0. So it will be R1 as R1 plus 3 by 2 R2 and R3 as R3 minus 22 R2. And based on that, what finally we will get is that 1 0 0 0 1 0. Of course, this will be 7 by 2, this will be minus 27 by 11, and this will be 0. And here it will be 4 1 minus 5. So look at this. Here we have done this. Okay, this we have already seen, but this is a new thing. See, there is a scope again to convert this particular column into a 0 0 1 kind of a column. So let's try that. Okay, so one extra step will be here that R3. Let's make it minus 1 by 5 R3. So what it will be? So it will be 1 0 0 0 1 0. This will be as it is because I am performing on R3 and all these elements of R3 is 0. So there is no change here, 0. But here there will be change 4 1 1. Now again the same steps. R1 will be equal to R1 minus 4R3, R3, R2 minus R3. Correct. So this is the next step which we will be doing. So finally, what it will be? So it will be 1 0 0. There is no change in a row reduced part. Here there will be change. Yes, it will be. I think Yes, this will be 0. So, okay. So, R3 is already 0. So, no need to change here. So, this will be minus 27 by 11. And this will be 0 again. So, now this will be 0, 0, and 1. So, now look at this. So, there are three rows for the augmented matrix. Remember, for the augmented matrix, the entire, there are three non-zero rows after the row reduction. Okay. So, your rank of A, the augmented matrix, which is equal to RA, is actually equal to 3. But if you look at this only, the matrix M, which we have calculated earlier separately, you don't need to do it. You can do it using the augmented one. So if you look at this matrix M part, you can see that two non-zero rows only, right? So rank of matrix M is equal to 2, which I have shown already earlier. So what we are getting then? We are getting for this particular question that R of n, the rank of the matrix M, is equal to 2, which is less than the rank of the matrix A, which is equal to 3. Interesting. Rank of matrix 2, matrix is 2, rank of the augmented matrix is 3. So Rn is less than Ra for sure. And how many number of, sorry, so if it is already less, so we have already seen that when Rn is already less than Ra, then it is having no solution. No solution. Now what you can try is that you can try to solve these three equations using whatever method, using substitution, using any method you try. Check that whether it is really providing any solution or not. So that is what is given here. So it will be a no solution kind of a uh, set of equations. Okay, it will not give any particular solution. So you can write it as inconsistent. Okay, this is number one. Another question we will do, another question we can try to see that whether we can get any other cases or not. But in this case, we will not separately calculate the rank of M and rank of A. We will just try with the augmented matrix, row reducing, and try to find out the rank of matrix M and rank of the total augmented matrix. Okay, so this is the second question which we will be discussing. So you have 5x plus 3y plus 7z is equal to 4. Second equation is 3x plus 26y plus 2z is equal to 9. And final is 7x plus 2y plus 10z is equal to 5. Alright, so this is the thing. Now, directly you write down the augmented matrix. You don't need to write your the actual matrix. So 5, 3, 7, 3, 26, 2, 7, 2, 10. So the augmented matrix itself consists of this, the matrix M. And with that, we are writing 4, 9, and 5. So again, I will do the row reduction. The steps I will mention, and you can do it on your own. That's fine later by just looking into these questions and try to solve. If you want to play with it, you can solve these equations on your own in the way we have done in the school levels, and then we check whether it is really following it or not. Okay. So the steps will be, say, the first step is that let's R1, let it be R1 by 5 because I need 1 here. Simple. Logic is simple. So it will be 1, this will be 3 by 5, this will be 7 by 5, okay, and this will be 4 by 5. The matrix will close it. Okay, this will be 3, 7, and it is 26, 2, 2, 10, 9, 5. Done. This is done. Next is you have to make these two elements 0. So R2 will be equal to R2 minus 3 R1. Similarly, R3 as R3 minus 7 R1. All right. Based on this, the first column you can easily reduce. So it will be 1, 0, 0 easily. Okay. And after the calculations, let me see with, yeah. So after calculation, you have 3 by 5. This will be 121 by 5, and this is minus 11 by 5. And finally, this will be 7 by 5. This is minus 11 by 5, and this is 1 by 5. Okay. And this will be 4 by 5, 33 by 5, and minus 3 by 5. All right. So this is after the second step of the operation. Next step will be what? To reduce this as 1. Okay. So for that, just use R2 as 5 by 121 R2. Okay. So it seems like a very difficult operation, but the questions will be given in such a way that you will see that it is easily chopping certain terms. Okay, you can easily chop certain terms, so it will be easy for you. Fine. So it will be 3 by 5. Look at this. This will be 1 and minus 11 by 5. So it will be as it is because no operation on R3. Here there is an operation. So this is minus 11 by 5. So it will be minus 1 by 11. This is 1 by 5 as it is. Okay, so this is 4 by 5, 3 by 11, and minus 3 by 5. Okay, based on that equation. Okay, next, same R1 will be now R1 minus 3 by 5 R2. R3 will be now R3 plus 11 by 5 R3. So based on that, let's see the new matrix. Let's write the new matrix. So it will be set 1 0 0. Here it will change now 0 1 0. What about here? This will be 74 by 55. This is minus 1 by 11. This is 0. This is 0. What about the augmented part? 7 by 11. This is 3 by 11. And again, here comes out to be 0. Okay. So you can see from here, uh, you will find, so you can see here. See, this is 3 by 11. So just put here 3 by 11. So 11, 11 cancels. So it will be 3 by 5. And here it is minus 3 by 5. Makes it 0. Okay, so in this way you can check. So this will be 0. So now look at the original matrix N, not the augmented one, only the original matrix N. How many non-zero rows are there? 2, right? So this is the matrix N. So rank of matrix M comes out to be 2 because there are 2 non-zero rows in a row reduced echelon form. Now, what about the total? When you have computed the entire augmented matrix A, how many non-zero rows you are getting? Still you are getting 2, right? This entire row is 0. So, your rank of the augmented matrix is again comes out to be 2. Excellent. So, Rn is equal to now Ra, which is equal to 2. Great. Two possibilities if Ra and Rm are equal. One is that you will get a unique solution or you will get an infinitely many solution. So what is this case? You know that there are three unknown variables here, x, y, z, right? X, y, and z. There are three unknowns. So, and but the rank comes out to be 2. So 2 is less than n, which is equal to 3. That is, there are three unknowns. There are three unknowns which are there. So x, y, and z. So there are three unknowns, but the rank of the matrix as well as the augmented matrix comes out to be 2. This gives you that it will be a case where you will have infinitely many solutions. Infinitely many solutions. So again, you can, if you want, you can try these three equations to solve using some different methods. You have substitution, whatever you want. Okay, and try to see whether you are really getting some kind of infinitely many solutions or not. Okay, so this is how you should proceed. So instead of, I would say that whenever this kind of question comes, just use the augmented matrix, row reduce it using these steps of operation. It will not take much time. It seems like it will take some time, but with a large amount of concentration, you have to do it because any small mistake will completely change the answer. Okay, so you calculate the rank of the matrix, rank of the augmented matrix, and just equate based on whatever the observations which I have written or whatever is written in the week 2 content. Okay, based on that, you can comment about the solution of the set of the equations. So this is how it has to be done. So we have seen two examples of this set of equations and how to say that the solutions will be, how the solutions will be based on the rank of the augmented matrix and the actual matrix. So the next part is about the determinant and the properties of the determinant, which is somewhat known to us, but we will also we will try to write it down properly. Okay, so this part is over. We will come sometimes like after calculating the determinant, after understanding the determinant, through the determinant also we can understand the rank and finally comment about the solutions of the set of equations. So that is the powerful way of looking into it. Okay, so let's see the concept of determinant. Okay, so very basic. Suppose you have a matrix M A, suppose, and you have some elements. Let us take the simplest of the example, A, B, C. D are some elements. It's a 2 by 2 matrix, square matrix. You can calculate the determinant. How will you do that? So determinant of A is cross. Okay, so it will be A times B minus B times C. Okay, so this is how the determinant is calculated. It's a simple way of looking into it. Now, another important thing is that with the determinant comes the cofactor. So, what is the cofactor? Cofactor is also a matrix. Okay, cofactor is also a matrix, and it is generally written as some C times Cij. The C is the cofactor matrix C. Cij. This I is the ith row, and J is the jth column. Okay, and we generally write it as minus 1 I plus j, and the determinant of the submatrices. I will show you with an example that what we are trying to essentially mean. Okay, so let us consider a matrix A, just an arbitrary matrix. Okay, yeah, I just so 1, 2, 3. Say this is 8, 9, and 4, 7, 6, and 5. This is a matrix. So how to calculate the determinant? I have shown it to you say in a 2 by 2 matrix or say 3 by 3 matrix. So to calculate the determinant, go through any row. Okay, go through any row. Suppose you are considering this row first. So write the first element 1. Okay, leave that column, leave that row. Whatever is there, you just calculate the determinant of this. Okay, so what is the determinant? 9 times 5, that is 45 cross. Okay, and minus 6 times 4, that is 24. This is the first part. Second is the second element which you will be taking, there is a negative sign of that. So minus 2. Again, leave that row, leave that column. So leave this row, leave this column. So you have 8, 7, 4, 5. So it will be 8 5s are 40 minus 4 7s are 28. Finally, 3. Okay, only remember the alternative elements is having a negative sign. So the third one will have these, right? So 8, 6, 48, 7, 9, 63. So if you just calculate, you'll get. So 45 minus 24, how much? It will be about 21, right? Minus 2. 40 minus 28 is 12. So 2 into 12 plus 3. 48 minus 63 minus 15. Excellent. So it will be 21 minus 24 minus 45. So 45, 24 is 49, 59, 69. 21 minus 69. 60, 21 minus 69. So minus will be there. and it will be 48, right? I think this thing. So this is how the determinant of the matrix is calculated. But how to calculate now the cofactor matrix? That is the next question. So just I am writing it again so that it is clear here. So it will 1, 2, 3. You have 8, 9, 4, and you have 7, 6, 5. Right. So how to calculate the cofactor? So just write it like this: C11, C12, C13, C21, C22, C23, C31, C32, and C33. These are the elements of the cofactor matrix. So how will we do it? Okay. So when we are calculating for the first one, that is 1, 1, leave this row, leave this column same. We just calculate the determinant of this. Leaving the first, so suppose you are considering this 1, 1 element, C11, you are calculating. In the A matrix, you leave this row and leave this column and just calculate the determinant of that. So it will be 45 minus 24, that is 21. Okay. Along with this, you just check this part minus 1 I plus j. So here I is 1, j is also 1. So minus 1 squared is 1, positive. What about 1, 2 is this element? Again, leave this row, leave this column. So it will be 8, 7, 4, 5. Take the determinant. So it will be 40 minus 28, which is 12. Okay. Check this. See, so it will be minus 1, 1 plus 2, because I is 1, j is 2. So odd number power of minus 1 is negative. So it will be minus. Okay. Similarly, C13, take this, leave this row, leave this column, you have this. So it will be 8, 6. So this is 6. Okay. Okay. 8, 6, 48 minus 60. So we have seen this is minus 15. And what about this? Minus 1 to the power 3 plus 1, 4, which is positive, right? So I don't need to multiply any negative sign. Fine. Next is 2, 1 here. Okay. So again, what we will do? Leave this row, leave this, so leave this column. So you have 2, 5, 3, and 6. So 5 to the 10 minus 18. So it will be minus 8. Now, minus 1 to the power 2 plus 1, 3. So it will be plus, opposite sign. 2, 2, this. Again, same, leave row, leave this column. So you have 1, 3, 7, 5. So 5 minus 21. So it will be about minus 60. So 2 plus 2 is 4. So it will be even. No need to worry. 2, 3, this one, right? 2, 3. So this and this will be gone. So it will be 1, 2, 7, 6. So 6 minus 40. That is minus 8. And again, you have 3 plus 2, 5, which is the odd power. It will be negative. So it will be plus. Okay. Similarly, 3, 1, do as it is. This and this you will leave. So it will be 2, 3, 9, 4. 4 2s are 8. 9 3s are 27. So 8 minus 27 is about minus 90. And 3 plus 1 is 4. The power is even. Here, leave this row, leave this column. So it will be 4 minus 3 into 8. So this will give you, as I write it, this is minus 20. But 3 plus 2 is 5. This is an odd power. So it will be positive. And C33 finally is minus 7. So this is your cofactor matrix. So you see the cofactor matrix is 21 minus 12 minus 15, 8 minus 16, 8, and this is minus 19, 20 minus 7. Okay, this is the cofactor matrix. All right, and now if you transpose this, so C transpose, if you do, this becomes adjoint matrix. So adjoint of a matrix is. Okay, so this is the adjoint of a matrix. Okay, so where is this adjoint useful? This is used to calculate the inverse. So generally inverse of A inverse is 1 upon the determinant of A times the adjoint of. So cofactor using the determinants is useful in calculating the inverse of the matrix. And where it will be used? So suppose you have say Ax is equal to B, some system of equations, then X can be written as A inverse B. So for that you have to calculate the A inverse. For that, this cofactor and this adjoint things are required. Okay. So this you have to remember that inverse will exist only when determinant of A is not equal to 0. If it is equal to 0, A inverse does not exist. Fine. So these are some couple of things which are associated with the determinant and the cofactors. Let's jot down the properties of the determinants and let's do a question on the properties of the determinant. So let me write. Sometimes what happens is that if you use the properties of the determinant, it is easier to calculate. Okay, so number one is that so the factor multiplied. I have just taken it from the notes only. Multiplied to any row or column. Determinant is also multiplied by that same. So if you multiply any particular row or any particular column with a particular factor, then the determinant will also be getting multiplied with that factor. Number two is that if your determinant is 0, when every element of some row or column is 0. If every element of a particular row or a column is 0, then the determinant is also 0. Also, this is possible if two rows or columns are proportional. This gives the idea of the linear dependence. If it is proportional or identical to each other. So suppose you have some vectors, suppose some 1, 2, 3, and next is 2, 4, 6. Okay, and then something, whatever, P, 4, 2. Look at this 1, 2, 3. If you multiply this row, sorry, this column with 2, you will get this. So this is proportional. So two vectors are somewhere linearly dependent. Here the determinant will be equal to 0. Okay. So linear dependence of two vectors, if you just put the determinant, you will find out that if the determinant is 0, then it is linearly dependent. Remember. So if it is the so determinant is one of the criteria to understand whether a set of vectors are linearly dependent or linearly independent. If determinant comes out to be non-zero, then it is linearly independent. If it is 0, then it is dependent. So this is one of the criteria, and this actually comes from the property of the determinant. The next thing is the third point is the determinant sign changes. When it will change? If two rows or columns are interchanged. So if you twice change the rows or columns, then it will be -1 into -1. It will be positive. So it will change. Okay, interchange or exchange, whatever it is. Fourth is the determinant of A and the determinant of A transpose is equal. There is no difference. Okay, so let us do one question to uh, just see certain properties, apply certain properties. Okay, so suppose you have been asked to calculate This is very known question actually. A, B, C. To find the determinant of this D matrix. A square, B square, C square. And this is 1 plus A cube, 1 plus B cube, and 1 plus C cube. This is very common questions actually in the school level or in the college level. So this is what you have to find out. Find out the determinant of D. So this is the question. So how will you solve it? You will use the properties of the determinant to solve it. Okay. So determinant of D can be written as like this. So it will be A, B, C. This is the starting point. So I'm writing it again, but the determinant symbol is like this. Okay, mod bracket, and this is 1 plus A cube, 1 plus B cube, 1 plus C cube. Okay. This first of all can be written as this A, B, C, A square, B square, C square, and you have 1, 1, 1. This plus this A, B, C, A square, B square, C square, and you have A cube, B cube, C cube. Okay. Just separating the additional part. You can do that. Okay. This is number one. Next is what? What you do next is that for the first part, you leave this as it is. A, B, C. You have A square, B square, C square, and this is 1, 1, and 1. Leave it. In the second part, look at this. You have A common from all this, B common from all this, and C common from all this. So you can take this. Okay. So A from the first row, B from the second row, and C from the third row. You can do it. The first property. So it will be what? It will be 1, 1, 1. This will be A, B, C, and this will be A square, B square, C square. Right? Okay. Next. Okay, leave this as it is. A, B, C, A square, B square, C square, and this is 1, 1, 1. Fine. Now here, what I will do is that I will exchange. So what I will do is that this I will put it here, and okay, so there will be minus sign because I am exchanging one column. So it will be A, B, C, 1, 1, 1, A square, B square, C square. So you will be understanding that what I am trying to do, I am just trying to replicate this determinant here. So for that, I am exchanging the rows. So A, B, C again. So this is A square, B square, C square. This is 1, 1, 1. Again, I will again add a minus sign and make it plus. Why? Because I will exchange this with this. So A, B, C, A square, B square, C square, and this 1, 1. That's all. So you see now these are all same. Okay. So now you can write this as 1 plus ABC times your A, B, C, or A square, B square, C square, 1, 1. This is how you can finally write. Okay. So now what you will do is that you can do some row reduction technique, like you can do R2 is equal to R2 minus R1, R3. You can do this, okay? R3 minus R1. So what it will give you? 1 plus ABC as it is, nothing to be changed. This will be A, okay? This will be now B minus A, this will be C minus A, this will be A square, this is B square minus A square, C square minus A square, and this is 1, 0, 0. Okay, so what you can do is that you can exchange it twice. So this here and then this here. So twice row changing or twice column changing will not impact the determinant. So you can write this 1, 0, 0. It's essentially the same thing. A, B minus A, C minus A, and A square, B square minus A square, C square minus A square. All right, this you can do. Now, if you have to calculate the determinant, use this particular column. This will be the determinant of this because two zeros are there. So it will be 1 plus ABC, and you calculate determinant here. Okay, so it will be the determinant of B minus A, C minus A, B square minus A square, C square minus A. Now further you can solve. You can take common B minus A from the first row and C minus A from the second row. Correct? So what you will get finally? It will be 1. This will be B plus A because B square minus A square is B plus A into B minus. C minus A if you take, it will be C plus A. Done. Now it's easy to calculate the determinant. That's all. I think it's done. 1 plus ABC. This is B minus A, C minus A. Now this you can solve. So what it will be? C plus A minus B minus A. So this is the final answer. 1 plus ABC, B minus A, C minus A, and B cancels C minus B. This is the final answer. So we have used so many properties. We have exchanged the rows or columns whenever we require by just multiplying a negative sign. Number two is that we have taken the factor common from a particular row or from a particular column. We have used the row reduction kind of a thing, row operations we have used that can be used, and that's all. These are the properties which one can use, right? So that's all. So yeah, finally this is the answer using the properties of the determinant. So this is how one can approach towards the final solution of the uh, determinant. When you have to calculate this kind of a large matrix, it is very difficult to uh, do the actual process of the determinant. Better to calculate using this. Okay, so now the next part is that we can calculate the rank of the matrix. We can calculate the rank of the matrix using the determinant. So how we will do, how we can calculate the rank of the matrix using determinant is what the next part we will be focusing on. So rank of the matrix using determinants. This is another way of calculating rank. So what we will do is that, so how it is defined is that the rank of the matrix, this rank is the order of the largest square submatrix with non-zero determinant. Okay, this is how the rank is calculated using the determinant. So I'll just give an example here to show that how to do it. So, so the question is that suppose you have a matrix M which is having this. So 2 minus 3, 7, 3, 1 minus 3, 2, 19, and minus 47. Okay. So I need to calculate the rank of this particular matrix. By the way, have I used this earlier? I think I have used in one of the row reduction techniques. Uh, yes, yes. So remember, I have used it here. See, this is the matrix. 2 minus 3, 7, 3, 1 minus 3, 2, 9. So we know the rank of the matrix, right? How much is the rank of the matrix? 2. Okay. So we will see that how we can look into this. Okay. So now, fine. So for this, what we will check is that you first take the highest order determinant. That means you take the highest order of matrix. What is the highest order of matrix possible here? 3 by 3 matrix. So the highest order is 3. So you take the entire determinant because this is the matrix which you have. So determinant of M is how much? That is first thing which you should take. So just do it 2 into this minus 47 plus 19 to the 57 minus minus plus 3, 3 into minus 47 plus so 3 into minus 47, yes, minus 20 plus 3 into 2 6, or I'm doing something wrong, I don't know. Yeah, it's okay, right. So yeah, 3 into minus plus 6, right, plus 7 times 3 into 19 minus 2. So if you do this, to calculate this, it will come out to be 0 most probably. Okay, so you just take it. So 10 to the 20, some way, just check. I think this and this finally result into 0. So this determinant of the 3 by 3 matrix will be 0. This proves that the highest order is not the rank. So this is having the order n is equal to 3. The order is 3 because you have taken the entire matrix, which is a 3 by 3 matrix. And we are getting for the order 3, the highest order determinant is 0. That means rank of M will not be equal to 3, the highest order. Let's go to the next highest order, which is order n is equal to 2. So there will be so many sub matrices. You have to calculate all those. Okay. I think there will be some 9 because 3 by 3 is there. So I think some 9 sub matrices will be there. You have to calculate each. So each of them, if one of them is non-zero, then that is the rank. Okay. So you take M1, suppose. Okay. So it is 2 minus 3, 3 and 1. Right? This one. Let's take this matrix first. So it will be 2 minus minus plus decreasing 9. So it will be 11, which is not equal to 0. Even if all others are, I mean, if any of the other submatrices, if it is 0, then the order cannot be 2. Means the rank cannot be 2. So you have to check each and everything. So, okay, M2 also you check, say some, say minus 3, 7, 1, minus 3. In that way, you have to check all the submatrices possible here. Okay, this, then 2, 3, 7, minus 3 together, then these two, like that way. So there will be so many matrices which will be there. So this comes out to be about say 2. I think this nth further if you go, so it will be 2, 7 and 3 minus 3. These are different matrices you can calculate. So it's minus 27. In fact, if you check all, it will be all zero, non-zero. So that, so all the second order matrices has or have non-zero determinants. And that proves that therefore, so now the determines, therefore, rank of M is equal to 2, which we have seen earlier. So this is how you have to proceed. But now, if any of these submatrices is having the determinant 0, then you have to go for the rank 1. Means you have to see that each of the elements. So since, of course, each of the element is 1, my means it is non-zero, then you will definitely get the rank as 1. You cannot get rank 0, except for all 0 elements present. Okay, so fine. Let's stop it here now. Next, we will go for another important thing, which is the Cramer's rule. All are used to what I would say to understand the solution of the set of equations. So this is a new thing, which is Cramer's rule. Interesting and very easy also to understand. So you have, suppose A1x plus B1y is equal to C1, A2x plus B2y is equal to C2. Suppose we are getting these two set of equations. Now, how we can find out x? Simple thing. Analytical, if you just go ahead, this is 1 and 2, just you, what you will do. So let's do this. Okay. Multiply 2, the second equation with B1, multiply the first equation with B2, and then subtract it. Okay. Subtract it, I mean 1 minus 2, let us do after this multiplication. What you will get? X will be equal to C1B2 minus C2B1 divided by A1B2 minus A2B1. Just try, okay? This is what you can do. Just if you multiply B1 here and B2 here, so this will cancel out. The Y terms will cancel. Only X and C1, C2 with some multiplication factor will be. And this is what we are getting. Now look into it very carefully. See, this can be written in terms of some kind of a determinant. Correct? This can be written, right? So how we can write? So X can be written as determinant of C1, C2, B1, B2. Check. So C1 into B2 minus B1 into C2, the numerator, divided by determinant of A1, A2, B1, B2. See, the determinant will be, this determinant will give you this. Okay, so this is how the X can be written in terms of the determinant. Similarly, for the Y, to get Y, the operation will be something like this. So you what you do is that you multiply 1 with A2 and 2 with A1 and subtract. Once you do that, you get y is equal to a1 c2 minus a2 c1 divided by same a1 b2 minus a2 b1. Again, this y can be written as determinant of a1 a2 c1 c2 divided by determinant of a1 a2 b1. So this is how the y can be written in terms of the determinants, x can be written in terms of the determinant. And as the number of order increases, you can just change the determinant order. That's all. Okay. So this is how, so the Kramer's rule essentially using the determinants, we can write the, or we can understand the solution of the set of equations. That's the major rule here. Okay. Fine. What else we can do? Okay, we have a small part of square system of equations, and then we will move towards uh, the span and the basis part, which is important, of course. Okay, before that, just a small thing, that is, suppose you have a square system of equation. Although we are talking about the square system of equations only, just quickly I can wrap up this. Square system of equations essentially means that it will be a 3 by 3 matrix or a 2 by 2 matrix like that. This is a square matrix. Okay. So suppose Ax is equal to B, writing the equations in terms of the matrix form in this way, where X are the unknowns which need to be solved. B is the right hand side of the equation, and A is the coefficients which is multiplied with the unknown variables. Okay, so what happens is that if you have this kind of a matrix form, you can again comment about the solution based on the determinant. So determinant of this A, if it is not equal to 0, then you have unique solution. See how many ways we can understand the solutions of your system of equations, right? We have seen using rank, we have seen using determinants, and there are many other ways also. Okay. Next is if determinant of A is 0. Okay. That means this is a square system, then rank of A is less than, we have seen that when the highest order, say 3 by 3 matrix was there here, When 3 by 3 matrix were there, I have calculated the determinant, comes out to be 0. That means rank is not equal to the number of unknowns. Correct? So that is what we are getting. Rank of A, the augmented matrix, or the matrix will be less than N. A means the matrix, not the augmented one. Okay. Then there are certain conditions that if the rank of this matrix A, if it is less than the rank of the augmented matrix, I'm writing now AUG, the augmented matrix, then again, so it's inconsistent. That is no solution exists. And again, so rank of A, these are known things, is equal to the rank of augmented matrix, and we have already proved that it is less than N, then it is having infinite solutions. All right. So these are known. These things are known. Only thing is that using determinant, how we can generalize it. Fine. And sometimes you might also have that this B is equal to 0. So something Ax is equal to 0. We call this as a homogeneous state of equation. Homogeneous state of equation. Okay. So that is your B is equal to 0. Okay. In that case, you always can have a trivial solution, that is x is equal to 0. This is a trivial solution. Okay. This you can have, and you have, again, it's the same thing, infinitely many solution when the rank of A is less than N. So all these things are there. You can check the notes also. I'm not going much into the details of this. Okay. And fine. The next thing is just a simple definition of the linear dependence and independence, because before the basis and the span, one must know some concepts about this. So linear dependence or independence. Okay, let's talk about this for some time, and after that we will go to the span of a span of a set of vector or basis. Fine. So for linear dependence and independence, so let us just assume a matrix, say 1, 2, 3, and 2, 4, 6. You can clearly see, as I have given the example, it is dependent. Okay, you can also write some 3, 6, 9, or something like that. Hmm? So you can see clearly that, okay, you can go ahead with 3, 6, 9, that is fine. Okay, so this matrix, of course, it is linearly dependent, very clearly seen. Okay, but I just want to remove this for the time being. I just want to keep it like this. Okay, so this is one of the vectors, this is another vector, this is another vector, composing this matrix A. Okay, and what about the rank? Rank here will be equal to 1. Why? Because, see, this is not a complete 3 by 3 matrix. So rank is not equal to 3 for sure. Now, take a submatrix, say this one, 1, 2, 2, 4. How much is the determinant? This is 0. Determinant is 0. If determinant is 0, that means the rank cannot be equal to 2 also. It will be the lower rank. And of course, if you take the element, it is non-zero, so rank is 1. Fine. Next is, the important thing is that take either row or either column. In whatever way you take, suppose this is, say, some U1, this is some U2, and this is some U3. Okay, so you know that your U2 is 2 times U1, correct? This is your U1. U2 is 2 times U1, and U3 is 3 times U1, right? So, of course, this U2 and U3 are dependent on U1, but you can set this U1 as one of the independent vector. This is one of the independent vector. Okay, one independent vector. Based on that, if you now multiply it by 2 or multiply by 3, you get a dependent vectors. Okay, so rank and the number of independent rows or independent columns are same. That is the thing which is to be shown. Another important thing that to check that set of vectors are linearly dependent or independent, you can go ahead with the determinant. If determinant comes out to be 0, that means it is dependent. We have seen it just here. But if it is not equal to 0, then you can comment that it is independent set of vectors. This dependent and independent set of vectors plays an important role in understanding the concept of the basis. Okay, but before that, we will go towards the span. So the concept of span is something like this. So it is span of a set of vectors. Okay, so these are important concepts. We will solve one question also after showing this. So suppose this is an example, written example I will show you. Suppose you have a vector say u. Okay, so you have a vector u which is 2 minus 1 and a vector v which is say suppose 3 1. Suppose, okay, this is just a ordinary example. So as you can see, u and v all belongs to or its span R2. So what does this statement means? So this vectors u and v, which I have arbitrarily written, I am saying that whether this u and v spans R2 or not. See, R2 is the field, okay, the real field, real number field. Okay, in that R2 real number field, which is having two rows or two rows and one column, kind of a thing. Okay. Now, each of the vectors in the R2 will be spanned by these two. What does that mean? So, U and V spans R2 means that I can write, so we can write, this means, so meaning we can write any vector, any vector in R2 as a linear combination of these vectors U and V. That's all. This is the meaning of the span. Certain vectors is spanning a particular set of vector represents that any vector in that certain vector in a particular set of vector can be written as the linear combination of those certain vectors. For example, if U and V spans R2, then any vector in R2 can be written as a linear combination of U and V. That's the concept of span. Okay, so how we can write? So C1 some constant times U. So what is that U? That is 2 minus 1 plus C2 3 1 is equal to some AB. I don't know, anything it can be. But this AB should belong to R. That's all. Okay. This is what the spanning means. Okay. Now we can also do it like this now. Just rearranging the things. Okay. This is a matrix. This is C1, C2, and this is AB. That's all. Again, you can come back to the original set of equations and try to solve it. All right, this is the meaning of the span. Now, what does it graphically means? Graphically, it means that suppose you have this coordinate axis. Okay, suppose you have this coordinate axis. Now, one of the vectors is what? 2 minus 1. So, I am arbitrarily arbitrarily writing it. Okay, so let's say 2 minus 1. So suppose this is 2 and minus 1 from here. So let us say this is one of the vectors. Okay, this is suppose x, y kind of a thing I'm writing. Another vector is 3, 1. So 3 and 1 somewhere here. Okay, so this is another vector. Okay, this is the second vector, say b, and this is the first vector, that is u. Okay, so any AB, whatever it is, I don't know. Okay, so any vector AB can be written as a linear combination of this. What does that mean? Suppose you have a vector AB as this, something, I don't know, whatever it is, any vector. What we can do is that we can multiply or scale using this C1. We can scale this vector U, and we can scale this vector V using this C2 in such a way that ultimately when we add, vector addition is being done, we get this particular vector. Understood? This is what we are trying to do. So what we can do is that if C1 is negative in some sense, so we can do something like this. This is your C1 times U, and V can be written as something like this, some C2 times E. And finally, when we join this in some way, we can say that this is your the result. Okay, this is what this trying to see. It is difficult to visualize. If we can put some values of A and B, then we can understand. Okay, so this is what is the main theme of the span. Okay, so any vector AB we can write as a linear combination of the vectors u and v. If we can show that, then we can justify that u and v are the two vectors which spans R2. That is any vector in R2. Okay, this is the meaning of this span. Just a rough example. Now, if we show in this spanning set, after proving, so after proving that and u and v spans R2, now if we further prove that this u and v are independent, that is mutually orthogonal or something like that, so independent, then we can say that this u and v forms the basis forms the basis for. So any vector can be written as a linear combination. Not only that, that u and v are independent also. Okay. So if it is forming a basis, it is absolutely clear that it will definitely span the set also. Okay. So just let's see whether we can prove it or not. So I know that C1 times your what is that? 2 minus 1 plus C2 times 3 1. Right? Proving independence is very easy. Just put the linear combination equal to 0. In the last class also I have discussed. Put that linear combination equal to 0. That means what I'm trying to say, C1U plus C2V, this is the linear combination, put that equal to 0. A and B elements are 0. This one. These are all zeros here. And try to see whether C1 and C2 are 0 or not. That's all. That is what we have to see. What it will be 2C1 plus 3C2 is equal to 0, minus C1 plus C2 is equal to 0. So C2 will be equal to C1 from the second equation. C2 is equal to 0, just put it here. 2C1 plus 3C1 is equal to 0, 5C1 is equal to 0, so C1 will be also equal to 0. If C1 is 0, then C2 will be what? 0. Therefore, this linear combination of u and v, if it's set to 0, we are getting the C1 and C2, the coefficients also equal to 0. That proves, this proves that U and V are independent. Okay, U and V are independent. Fine. So this will show that U and V forms basis for R. Okay. So this is what. Now my idea was that if we can just show this graphical representation using some A and B value. So some, let's say we can take uh, say one, it is A is one and or A is minus one and B is one, suppose. Let's see whether we can I just can show it or not. So this is your something that arbitrarily just I'm trying to show. This is the thing and this is another thing. This is U and this is some B and this is minus 1 1. That means uh, x is minus 1 and B, that is y, is somewhere 1, right? Somewhere here. Okay. So for that, I mean, you have to, of course, calculate all these things. Just check that what will be the direction of the U and V. You will see that the C will be, sorry, C1 will be negative, so that U will become something like this, and the C2 will be something like this. So when you do the parallelogram law of vector addition or triangle law of vector addition, you will generally get this. So you can put A and B and check it later. Okay. So this is what it essentially means. So any vectors, whether it is minus 1, 1 or 1, 0, 0, 1, whatever, this U and V will be scaled in such a way that it will always add up to get this particular vector. That is the meaning of span. But now this U and V are, if they are independent, then they form the basis. That's all. Okay, so let us just uh, write a question and try to solve it. Then that will be clear. Then other things, if time permits, then I can go ahead. But this is important, so that's why. So one question for the spanning and the basis, let's do. So let V be the vector space R3 and let V1 given by 1, 2, 1, V2 given by 1, 0, 2, and V3 given by 1, 1, 0. Okay. So now S is some set like V1, V2, V3. Question is that does this set of vectors span V or not? This is the question. So V is the R3 vector space, is a field, real vector space field. And this S is also a set of vectors, which is given like this. Question is that whether S spans V or not. What is the meaning of that? Can we write? So the meaning is that can we write any vector of vector belonging to vector space V as a linear combination of these vectors v1, v2, and v3. That's the main question. Okay, so let us take a vector v, which is the x, y, z, which belongs to the vector space v. Okay, or R3. So thing is that it should be C1 V1 plus C2 V2 linear combination plus C3 V3, which is equal to V. Alright, so just write it down. So C1, what it is, 1, 2, 1, the vectors, okay? C2, 1, 0, 2, and C3, 1, 1, 0 is equal to your x, y, z. Perfect. So just write down the equation C1 plus C2 plus C3 is equal to x. Just quickly do this calculation. 2c1 plus 0 plus c3 is equal to 1. c1 plus 2c2 plus 0 is equal to z. Just multiplying the c1, c2, c3 with the equation. So what we'll get is that C3, I'm not solving too many things, just I'm writing the whatever I'm getting the final result based on x, y, z. So C1 comes out to be 2y plus z minus 2x divided by 3. C2 is x plus z minus 1 by 3. And C3 is 4x minus y minus 2z by 3. So, as you can see, we can write C1, C2, C3 in terms of the vectors A, B, and C or X, Y, and Z, whatever. Therefore, it shows that we can write for any X, Y, Z, we are getting C1, C2, and C3. So, therefore, we can write the vector V as a linear combination of vectors in S. Therefore, S times V or R, whatever. So this is how you have to proceed. The next question is that whether these vectors forms the basis or not. There is the second question. Obvious second question is this: whether the S vector forms the basis for R3 or whatever. Okay. So for the basis, already I have shown that S spans V. Just for the basis, we need to prove the linear independence, right? So once you do that, it will be done. Okay. So now, uh, let's see. Okay. Yeah. So x, y, z will be 0. Let's try this one. Although I have. Okay. Let's forget about this. Okay. So C1 plus C2 plus C3 is equal to 0 as the first equation. 2C1 plus 0 plus what is that? C3 is 0. C1 plus 2C2 plus 0 is equal to 0. Right? This is what you have to do. Now, yeah, just solve it. That's all. Let's see whether it forms basis or not. So C1 will be equal to minus 2C2. C3 will be equal to minus 2C1. Okay. Now we can put it in the first equation. Let's see. C1 plus C2. C2 can be written as minus C1 by 2. Okay. And C3 is minus 2C1. That is equal to 0. So in some way you are seeing that some constant times, so it will be 1 minus of will be half minus 2, that is minus 3 by 2, C1 will be equal to 0. Right? Yes. Right. So it's minus 3 by 2, C1 will be equal to 0. So C1 should be equal to 0. If C1 is 0, put it in C3. C3 will be minus 2 into C1, which is 0, that is 0. If C3 is 0, okay. If C3 is 0, then let's see whether we can. Yeah. So, okay. If C1 is 0, of course, this C2 will be also 0 from here. So, all these three things, like C1 is equal to C2 is equal to C3 is equal to 0, proving, proving the linear independence. Okay. So, this, therefore, S forms basis for R3. Okay. So, this is done. I have another example, but let me just uh, skip that. Just wanted to show some more things. Although those are written in the week two. So I just can write that question for the typing. If later you can solve. Okay. So just the set of vectors have changed. So it is 1, 2, 3, 0, 1, 2, and minus 2, 0, 1. This, whether it forms, just check whether it forms a basis for RQ. Okay, this you can try it. So this is the question. You try. You'll see that it will form a basis. Just try it out. Of course, you have that assignment questions also, so that you can, of course, do. We can solve those questions in the next class once the period of assignment is over. After that, we can solve. The next class we can solve. Okay. The next topic is uh, Gram Schmidt orthogonalization. This is just a technique, just a formulation which is being provided, not very important, but just I wanted to discuss that what essentially it tries to mean. So this is the original basis B. They're saying that it consists of some vectors x1, x2, so on up to xn or n. Okay, so these are forming actually a basis. Okay, this is the original basis I will say. Okay, the original basis for the set of vectors S, which has e1, e2, so on up to en. Okay, so what they are saying is that this S vector, each vector in S can be constructed such that each vector I, that is e1 or e2 or e3, is a linear combination. Of course, because that is forming a basis, that means combination of vector of B. Right. That itself means that B spans S. Okay. And it forms a basis because these are linearly independent vectors. Now, what happens is that we can use this and ortho normalize that to form a new set of orthogonal bases. So C is suppose a new set of orthonormal bases because they will be normalized. Orthonormal basis is a new set. Okay. So how we can write? So the new set will be say some E1 that will be x1 divided by the norm of x1 oblique x1. So it's inner product. You can see that this is the norm of x1. So this is how you can make the first vector or in the C orthonormal basis set. Next is E2 dash, the new one, E1 dash also you can write, that's fine. That will be x2 minus E1 x2 E1. So this is how it is being created. They have people have seen it, that they have observed it, that through this we can create a orthonormal set of vectors which will be now called as the orthonormal basis. Originally x1, x2, x3 are some basis. Now it will be the new basis will be formed using this. Okay, and so the vector e2, I mean this is e1, let it be. So E2 will be now this E2 dash, whatever you have found out, that divided by E2 dash, E2 dash. So these are all steps which you have to follow. Similarly, E3 dash, first you have to find, that is X3. You can see that it will follow a pattern. E1 X3, E1 minus E2 X3, E2, Okay, this is E3 dash. Then E3 will be then what? It will be simple E3 dash divided by root over E3 dash E3 dash. Okay, in that way you can follow. Just keep on adding the terms and try to build up this. Although I have not found much of questions from this, and I don't think in the assignment so many too much questions are there. But if you have to generalize this, let me just write it that you first find out ei plus 1 dash any arbitrary I. So it will be x j plus 1 minus summation j going from 1 to I ej x j plus 1 into ej. Once you have done this, ei plus 1, the actual vector, will be ei plus 1 dash divided by the norm. Okay, so this is just a formulation. Can't explain much of the meaning of this. Okay, so this is one of the techniques to orthonormalize the vectors. Fine. Let's go for another important thing, which is the vector subspaces. Questions can come from here also. Vector subspaces. Means the typical question is that prove that this is a subspace or of a linear vector space. No. Okay. So let just quickly give the example. So V is a linear vector space, and let us say S is a subspace or set which is a subset of V, the linear vector space. B is subset of vectors in V satisfying the following requirements of a vector space. Generally, in vector space, we have seen that there are certain requirements like closure and addition and multiplication, scalar multiplication there. So here you just have to prove the closure under addition and closure under scalar multiplication. That's all. You don't need to prove that zero exists or something, but scalar multiplication. These two will be enough to prove whether any vector, a vector set is a subspace or not. Just prove that. Okay. So it will be some alpha times whatever it is, b1 plus beta times b2. This should belong to the actual space B. This is what we have to do. Okay, so this is what it is. Finally, there are certain things. Let's discuss for 5 more minutes and then we can wrap up. Some linear operators are being introduced. Linear operators. Okay. So one of the things is that suppose you have a vector x. Now, if you operate, suppose A is some kind of a linear operator. If you operate this A on x, you will get some y. Actually, what you know in when you will when people study about the quantum mechanics, whatever the matrix equation we generally write, that is Ax is equal to some lambda. Okay, this is what we generally write. Right? This is the eigen values, and these are the eigen vectors. So what we say is that A is some kind of an operator. Okay, this is some kind of an operator, maybe some quantum operator or something. In the quantum mechanics, generally we try to interpret in this way. This A matrix is an operator, some quantum operator, which is operating on this vector x. Okay. Okay. So any operator which is operating on vector x, which gives lambda as the value of the operated vector. Okay. So Ax, this gives you the actual scalar value. Okay. Or the magnitude. Suppose this A is the energy operator, the quantum energy operator. So this energy operator is being operated on certain vector that gives you a scalar value of energy and with the multiplication of that particular vector. Okay, so this is how generally these operators being used. So suppose x belonging to B, y also belonging to B. This is just an example I have given. So this is how the linear operators. So how linear operators work? So if this operator is being operated on this alpha times x plus beta times y, where x and y belongs to some vectors B, this can be written as alpha times a of x because this operator will always act on vector, not on the scalar. Scalar will come out. So alpha a operated on x plus beta times a operated on y. We will not write a multiplied by x, but we will say that this linear operator is being operated on the vector x or operated on the vector y. This is how you generally. Okay, so this is the thing of the linear operator. Another important thing is that there are inverse operator. People say left inverse, right inverse. I don't think much of a meaning lies on that. You can easily say that suppose x times a is equal to I. What you can do is that so you can I think this you can write if a into a inverse is nothing but a inverse a, which is equal to I. This is a very simple property which you can easily deduce. So let's see. Uh, Let us try it. Say suppose a inverse a is equal to I. We know this. Okay? A inverse operated on means this is the operator, all are operated. So A inverse matrix A is equal to I. We know this. Okay? So it is a starting point that we know. This is the now what I will do is that in this, if I multiply A to its left, it will be A times I. So it will be A inverse A, which is equal to okay. So this is what you can write. So this A times I, this can be written as I times A as well. Correct. So this A into A inverse A can be written as just a minute. Yeah. So A times A inverse A can be written as I times A. Now what I will do is that this A inverse minus I times A can be equal to 0. Okay. So based on that, we can just say that this A inverse is also equal to. So this proves that A inverse and A inverse A are same. That is the identity. So here comes another operator called the identity operator. So just people are naming it identity operator. Okay. So there is an expression of this identity operator. You can refer to the notes. I'm not going into much details because of the time cost. Okay. So this is how the operator is given. I think this is the end also. This is the this is the cat bracket, this is the bra bracket. So be careful. This is an operator. Okay? This will be operating on something. So suppose you have to operate this on EJ, which is an orthogonal set of vectors of EI. So you have to write like this: I is equal to 1 to n. This is EI, and this will be EI EJ. So you know that this comes out to be the delta ij because if I equal to j, then only this delta ij equal to 1. Correct. So finally, you will get that this will come out to be 1 only when I is equal to j. So it will be j. So any vector of if the identity operator is operating on any vector, it will be the same vector. That's the major thing. So here I is equal to j means here only one value will be there. So e of j. That's all. Done. This is done. And the last thing is that the adjoint of a linear operator. Okay, so I'll just give you a quick thing. So adjoint. Too many things are given in the notes, but I'm just giving the example of this. Okay, adjoint of a linear operator. See, this adjoint here is not that thing, but it is the Hermitian conjugate. You might be knowing about the Hermitian matrix, where A dagger we say transpose conjugate. So that is what is this particular operator is conjugate. Okay. So suppose L is a linear transformation going from some vector space to another vector space. Remember, this is an operator always. Okay. So what happens is that uh, adjoint of this linear operator L is an operator. Remember, is an operator. Adjoint of L is also an operator, which is L dagger, such that how we can write this, such that L dagger we can write L dagger x y is equal to x L y. So L is a linear transformation or linear operator. Adjoint of this linear operator is L dagger, which is also an operator, such that we can write this expression. Or x and y are, of course, x and y are some vectors from vector space. So just one example to end with. Say suppose V is coming from R2 real space. So L of x1, x2, suppose x1, x2 is x2 comma 0, some kind of an operator which gives you this. Okay, and in dagger, I just wanted to prove that is suppose 0 and x1. Now you will see that when you see this one, suppose x L1, you will get what? See, this is a Bragg kind of a thing, notation, so it will be x1, x2 transpose, and this will be the L of y, that is y1, y2, which will be y2, correct? 0. Just put in here, instead of x, it will be y, right? y1 and y2. Similarly, L dagger x, y can be written as, so L dagger x is 0, x1, but it will be in a bracket, so it will be 0, comma x1. What about here? It will be y1, y2, simple y vector. So in both the cases, you will get this as x1, y2. In this case also, it will be x1, right? So these two are equal. That is what I try to show based on that is example of L and L dagger. And certain properties. Number one, a dagger of dagger, my adjoint operator of A, its adjoint gives you A. Number two, A plus B whole dagger is A dagger plus B dagger. This dagger is the Hermitian conjugate of the adjoint of the operator. Number three is AB whole dagger is B dagger, B dagger, and fourth C times some A dagger is the complex conjugate of C and 8. That's all. These are certain properties which is useful. Okay, so with this, I think we can stop here and we will do the assignment. And once I think tomorrow is the last day. After that, the next week we can solve some questions from the assignments that will clear many other concepts. Okay. And okay, if any questions are there, you can ask today or next class when we solve the assignment. I can take that questions. Okay. So with this, I think I can stop it here. So genuinely, I have given certain ideas so that it becomes clear, particularly the span, the basis, and about the systems of equations. There are three categories of solutions, which we can see through rank, through determinant, and many other processes. Okay. And finally, we talked about some vector subspaces and the operators. That's all. So the basic idea I have tried to give. Fine. So with this, I think we can end this content I will upload. Fine. Okay. So we can stop. If you have any question, you can ask. Okay. Thanks.